All right. Hello, everyone. I'm Rijnard. Welcome to this talk on bug hunting with structural code search. I'm happy to have a slot after lunch, so I'm not between anybody and the food. Before we get into the details, a little bit about me. So I graduated with a PhD from CMU this year, where my research focused on program transformation, program analysis, and program repair. Program repair is also known as automated bug fixing. I now work at a company called SourceGraph, where we do code search, code intelligence, and large-scale refactoring. I'm very lucky because I get to apply and implement a lot of the ideas that I had in research into practical developer tools. I work remotely, and I'm based here in Phoenix. I'm here with a coworker too, so if any of this sounds interesting to you, do reach out after the talk. So this talk is about code search and hunting for bugs. A lot of you are probably familiar with grep. So grep is a regular expression-based search that works on plain text. It's good for bug hunting. A lot of people have used grep to initially find patterns of code that look suspicious or find buggy code. And so I want to run with an example of one pattern that I simplified that was used in the past to find some buggy code in an SSH library. There are more details about this in the link at the bottom, and you can get the slides afterwards from me if you're interested in delving more deeply into that. But just at a high level, looking at something like grep, a pattern like this, what does it mean? It's not obvious reading it, what's going on here. It's kind of like Perl. You can do anything with it, but it's not necessarily the easiest thing to understand. And so really what this pattern is doing is it's trying to identify snippets of code like this one, where there's an allocation. So some call is allocating memory, and there's some user-controlled input that flows into the size of the allocation being made, and that can be a very large number. And that can lead to a buffer overflow down the line. So this pattern was used to identify this fragment of code, and what I've highlighted up here in the slide are all the parts that don't refer to syntax, right? So it's meta syntax. So we have things like this asterisk that says, well, we want to repeat matching a bunch of characters, and in a different context, we have an asterisk that actually means we want to match this asterisk in the code because that's a multiply operation, right? So there's a lot of parts here that we have to get right to match the thing that we care about. And a lot of this pattern going on here in the middle is the idea that we want to match arguments inside of parentheses. And it's hard to do that just off the bat with grep because you have to take care of a lot of things, otherwise it keeps matching past some parentheses or semicolons, so you end up matching too much or too little. And the point here is that code structure matters, right? If we're interested in matching things like expressions or blocks in code, then it becomes tricky if we are using just a plain text approach. And so the whole question around a structural code search is, can we identify patterns around the structure of code a little bit better? So stepping back from this pattern, I'm going to talk about Comby, which is a tool that I wrote that enables you to match structured code and then also rewrite it. But for the purposes of this talk, looking at how we can functionally do the same thing as what this grep pattern is doing, here's the meta syntax in Comby, where, again, I've highlighted the parts here that don't refer to the code that we're trying to match. So here, there's a syntax that binds holes to identifiers. Here I'm just using the identifiers 1, 2, and 3 to refer to arguments and parts of an expression in the arguments. And the rest of this pattern is all concrete syntax, so there's no escaping or anything like this. Besides the fact that it's a little bit more readable than grep, there's a really important property here, which is that these parentheses are balanced, and there's this baked-in, built-in understanding with these code patterns that for a particular language, you cannot match across broken parentheses or braces or brackets. And that's really an important property of code structure that we'd be interested in matching. I'm going to go into more detail about those examples soon. It's also language aware, so for each language that you may be using, Comby understands comments the different kinds of comments, and so this pattern won't match comments. And all of this understanding is baked into a bunch of languages. It probably supports the language that you're using and a bunch of DSLs, because it has a kind of generic way of matching these sorts of things. In this talk, I'm going to be primarily looking at bugs in C, and one example in Go code, but it generalizes. So C is a really good language because there's lots of fun bugs, and I think especially for security researchers, C is a go-to target. So to give a kind of high-level impression, just, this is a tool that we run on the command line. Here I'm just showing you how to run one of those examples with the alloc function from before. So there we go. This is just typing that structural pattern on the command line. It's being wrapped by a utility that highlights the code, and so you can see that it identifies some of those patterns, and that includes multi-line matches, right? So you don't do anything special. Spaces are also considered white space, and that can cross multi-lines because we know that things inside parentheses are captured. There's no special logic that you have to add to the pattern. So let's look at an example in the Linux kernel. So pretty recently, there are some new CVEs reported for the Linux kernel based on melody references from failed memory allocations. So here's a high-level description. What's going on is that memory is allocated using a function allocWorkQ, and it's not being checked, and so that can lead to a melody reference and kernel time. So I'm going to run through an example of how we might do this with the structural pattern matching in Comby. So here we might be initially interested in matching function calls. So syntactically something like this, where we're looking for allocWorkQ and then some number of arguments. And again, so this won't match comments. So you'll find that a lot of noise that you sometimes use to grab that matches things like comments or strings that you're not interested in. And so this matches 274 calls in the Linux kernel, and those are actual calls. And if we think about, well, what's the property we're interested in checking, one thing that we could do at a very rudimentary level is say, well, in the good case, code like this usually gets checked with an if condition afterwards on the thing that is being assigned, the pointer being assigned from the allocation. So in Comby, the way that we can expand the existing pattern is to say, okay, we're going to match on this word coming after this if expression. And we're going to say that, well, if this word coming after it is not an if, then that could be potentially suspicious. So rules are a separate constraint language in Comby. It's not mixed into the initial template, and that helps to cut down on the amount of meta syntax that you have to put in. Well, if we use this, we're going to still get some false positives and noise in the kernel. You find that there are other ways of checking this property. So sometimes there's a call like bug on, and this flavor also checks that no bug or melody reference will occur. So we can add to that constraint language to also remove matches where we see something like bug on in the next word. Now we can continue to refine this. There's still some other cases to handle, and you can actually get much more refined and say, well, I actually want to check that the variable being assigned here is also checked. But I want to stop here to just kind of communicate, again, the flavor of how this works. If we stop at this point, you'll find that there are only 38 calls left to check through. And Comby is quite fast, so if you run this on your Linux or on your laptop, it'll take like 1.5 minutes. So this is a lot faster than running a deep static analyzer. And you'll find real cases. So this is one case in the Linux kernel that I think is not addressed or fixed yet. So if you want to make a contribution or investigate that more deeply, you are more than welcome to. And it finds the existing cases that have been reported with CVs and still not checked yet. There are lots of these kinds of bugs or patterns, right? allocWorkQ is just one of many kinds of functions that perform the same idea of allocating memory and not being checked. And this is also a very recent patch that fixes this federal bug. So there's a lot to discover out there. And there's another case in CPython. CPython is the Python interpreter for the Python language. I just covered this case. I gave a commitment to null check. I haven't submitted it. If somebody else wants to, you're more than welcome to. A lot of things out there with this kind of flavor. So those are some C examples. Let's move on to something a little bit more different. So I'm going to look at an example in the Go language for Kubernetes. Up till now, you might be able to convince me that grep is good enough still for what you want to do, and so this example will hopefully convince you that you can do some richer things more easily. So in Kubernetes, there's still an open issue about integer overflow. When parsing integers from user inputs or configuration files, what happens is that we have code like this, where there's this parsing operation. It parses an integer as a 64-bit width integer and is assigned to some variable. But later that variable is converted to an integer with fewer bits. So we lose information. And what this means is that the integer could overflow. So if you look at this issue online, you'll see there's this really nice example where if you specify this very big port number of the Kubernetes tool, it'll overflow and will actually overflow to the number 81, and then when you run this configuration, it'll open up the port 81. So this is the sort of thing you want to avoid, right? It's just not good practice. And so how could we detect a pattern like this using Comby is the next part of what I want to talk about. So we have this function, parseInt. We're particularly interested here in calls of this function, parseInt, where the third argument is, for example, 64. So we know that we are parsing input, which we're going to treat as an integer with 64 bits. And I'm going to bind that to a variable v on the left-hand side. And again, I'm using that syntax to say that this is a word. So it's some identifier that we're assigning to. So in the code at the bottom, you can see what's being matched. Then what I'll do is I'll add another hole here to say rest. And this will just bind to the rest of the code in the function. So I've highlighted that below. And so one notable thing here is that this rest stops matching within these bounds delimiters, within these braces for the function. And as I mentioned before, that's kind of the intent here is to only match within well-defined blocks or expressions with respect to the syntax of the language that we're matching on. So we can refine what we're interested in the rest of this function by using another flavor of this match rule. So before I showed you, we can check whether something we found is syntactically equal. We can also pattern match against things in holes. So this is a nested match rule, so we can nest on the matching of things that we've matched before. And in this syntax, we're matching on calls like int32 that perform this cast, right? So, and what we're going to do is we're going to look at the argument being bound in that call. So that's going to match this argument parsed in the rest of our function. I've highlighted that. And then we're going to check whether this argument is equal to the thing that we assigned before. And because we're in the same function, we have a reasonable confidence that this is going to be the same variable because it's in the same function scope. So there might be some noise here, but in general, this is a good kind of easy way to go about looking at data flows without writing any heavyweight tooling. So that constraint checks that these two pieces of syntax corresponding to an underlying variable are the same. And we can extend rules like these to match more codes that we're interested in. In this case, maybe we're also interested in matching functions that convert that integer to a 16-bit with integer. All right, so here I've just pre-populated it on the command line just to show you that you can write this all out on one line, the pattern and the rule. When you run this on Kubernetes, you'll see a lot of blocks of text where these conditions hold. So inside of these blocks, you'll see a bunch of cases where an integer is being parsed and then used after a conversion. So that's it for the demos. Taking a higher level view just of what I've talked about a little bit. So structural code search is this idea of just making it easier to search across syntax trees rather than sequences of characters, and to kind of extract out the parts of your code that are structured with respect to those syntax trees. So the idea here is to cut down on the effort that you're putting into, so something more grep-like and something less like a query language or a heavyweight solution where you're writing some scripted program to actually introspect on the tree. The idea is to have a general solution that works for all languages by default, and then to refine that based on the syntax at a language-specific level. If you're intellectually curious about more of this stuff and what's going on underneath the hood, you can check out a paper about this. Find that afterwards, or come talk to me if you're interested about that. And that goes into a little bit more detail about the complexity, precision, speed around the tooling. So, in summary, I introduced this idea of, grep is a good bug hunting tool for patterns in code. Code structure matters when we try and find these buggy patterns. Can we do better? So Comby is a tool that I wrote that reduces the amount of meta syntax that you have to use, and also helps you to match on things structurally. So I've given examples: C code, Linux, C Python, and also showed you how you could apply this to a language like Go, the Kubernetes project. So you can find a lot of resources online. Usage documentation at the website here. Go on GitHub, maybe start it so that you can remember that you want to talk about this and try out this tooling. Any questions, please come on the Gitter channel. I'm pretty active. I will try to respond within a couple of hours. And I will make these slides available, well, they're already available at the URL over here. So thank you so much for your attention. I'm happy to take any questions. We have a couple minutes left for that.